So the last part of Chapter 8 will be a look at the strength of covalent bonds. We actually have a live audience today for the recording of this one. So the bond association energies are given for several elements up here. Now it's important to remember that these are energies to break bonds when the elements or when these bonds are in the gaseous state or when these species are in the gaseous state. Obviously the forming of these bonds then would release that same amount of energy. So for example, if we had an oxygen molecule in the gaseous state and we wanted to look at the energy it took to break that apart, where's our O2? Here's the single O to O bond. Here's a double O to O bond. Oh, here it is right here. Okay. So it would take 495 kilojoules per mole of those molecules to break them apart. Or if we formed a mole of those, we would get 495 kilojoules of energy back out again. Now, if we apply this to reactions, now granted we have to be a little careful with this in that this is only going to work for, work to precise state for reactions that are happening in the gaseous state, but we can get a good idea of the delta H for reaction by applying this idea. So we take the energies that we need to break the bonds, right? And we're going to, so that would be the vertical part here, going from the methane and the chlorine in this molecule, breaking off one of the hydrogens and breaking the two chlorines apart. So that would be the bond breaking, so that's how much energy we have to put in. And then we would subtract the enthalpies of the bonds that are formed, which would be the hydrogen to the chlorine and the carbon to the chlorine. And in this case, once we figure out the numbers, we'll actually get out more energy than we had to put in to break the bonds. So we'll take a look at that calculation next. When we put this into a longer formula, we have, again, right here, the bond association energy for the reactants, the bonds that we're going to break. And we're going to subtract the bond association energy of the products, the bonds that we're forming. Where do we get those values? Well, again, we can go back to our table. And we had the carbon to hydrogen that we had to break. And we had the chlorine to chlorine that we have to break. So those are two energies that we needed to break. And then the ones that we're going to form is between a carbon and a chlorine and a hydrogen and a chlorine. So those are the numbers that we'll put into our formula then. See, once we do the calculation, then we end up with the number of kilojoules that would be given off in this reaction. It's kind of fun to apply this to a couple of explosives. So in the top picture we have nitroglycerin. Notice that the explosions are just, combustion reactions. So remember, combustion reactions are going to produce carbon dioxide, CO2, water, and in this case, in the case of these, we're also going to produce nitrogen, N2. Now remember that the N2 molecule is going to be a triple bond between the two nitrogens. That's a very stable state, so we've gone way, way down in terms of stability state. So we can see that both of these molecules, the nitroglycerin and the trinitrotoluene, will go way down in terms of bond energies. So they release a lot of energy. The other thing we can apply this to is the bond length. Remember we talked about the more electron density we put between the nuclei, the smaller the bond would be. So we go from a carbon single bond to a double bond to a triple bond, and we see that those keep getting smaller and smaller. And if we go back to the bond energies, we would see that the bond energies get much larger. So we look at a carbon-to-carbon single bond right here, which is 348. Carbon-carbon double bond, almost twice as much, and a carbon-to-carbon triple bond up to there. Now remember that we are going to get into the bond, the valence bond theory, and we'll see that these aren't exactly doubles. I mean, the pi bonds are a little bit different than the sigma bonds, so they aren't going to have quite as much energy associated with them once you go to the double and the triple bonds. So it's not twice as much. All right, so that finishes off our chapter 8, and then we'll begin ready to go on to shapes of molecules in chapter 9.